Now let's look a little bit at the circuitry in the row. So what is the row? So if you think about the SRAM architecture, the SRAM has a row decoder, and the property of the row decoder is it needs to, based on the address that I've given, it needs to select a particular word line. So what we're doing is we're decoding an address across the various word lines. So very simply, if I want to implement a decoder, I implement it using a NAND 2 and an inverter. So in this case, if I have a 2-bit address, I can decode it into 4 word lines. And I want to ensure that I need to size them appropriately, because depending on the size of the word line that I'm driving, having a 2-stage or a 3-stage will allow me to share the load comfortably and get a minimum delay for this path. Now word line needs to be qualified with the clock for proper timing, right? And so which means that if we have a large memory, then the size of these inverters have also got to go up, and which means that the leakage or the static power leakage in all these inverters is also going to go up. The other important requirement is going to be from layout of the decoder, is that the decoder cell should be pitch matched to the SRAM. Remember, SRAM is tight, right? And because the entire SRAM has to fit within a small area, you don't want the size of the SRAM to be limited by the row decoder or the column decoder. So hence another requirement that is put on designers is that the row and the column decoder and the column circuitry, all of them will have to be pitch matched to the SRAM bit cell. So that puts further restrictions on the way you design this particular decoder. So this kind of a decoder works well for only about 5 or 6 word lines. If you have a larger memory, we use what is known as a pre-decoder. So when you have a larger memory and you have a lot of word lines, you'll see that the decoders typically have a huge branching effort and hence a higher path effort. And so which means we need to add stages to minimize the logical effort of the decoder. So if I look at a 16-word decoder, if you think about it, you're going to have basically 4 address lines, and you're going to have 16 such circuits to generate word line 0 all the way to word line 15. Right? And so you see a lot of branching that's happening across on every line that is coming from the address bit. So one way to optimize this would be using what is known as pre-decoder, where we factor out all the common NANDs. So we create these partial decoded signals, if you will, and then we combine those into the word line. So in this process, by sharing a bunch of pre-decodes, we are able to reduce the logic branching effort and hence the logical effort across the path, leading to a faster decoder. So this is commonly used in large memory decoders. Now one word about the word line. The word line is running across the entire memory, so it has a very large capacitive load. And when you're designing for minimum delay, the NANDs have to drive this large load. And so placing a buffer between the decoder and the word line saves a large amount of dynamic power at a small cost of delay. So you can hear we're slightly increasing the delay, but by reducing the size, we're able to save power in the SRAM. Now, many a times, because these word lines are very long, sometimes we use what are known as hierarchical word lines to manage the delay. And that is because we want to keep the word lines in the lower metal lines. The lower metal lines have lower capacitance but have high resistance. So what we do is we have what is known as a global word line and a local word line. So it would look something like this. You have a row decode which gets you to the global word lines, and then you have another column decode, a combination of those two which will get you to the local word lines. And what we do is the local word lines are in lower metal, so they're going to give you, they're going to drive less number of gates, but they're going to be quick. And the global word lines which have to go over long distances, they're going to be done on higher metal with lower resistance. So a combination of those two will eventually use to reduce the delay on the word line. Now let's look at the column circuitry. So the column circuitry has 4 major components. The first one is the bit line conditioning. So this is required to pre-charge the bit lines high. Then you have a write driver, you have a bit line sensing circuitry, and you have the column muxes. So if we look at the bit line conditioning circuitry, it is required to pre-charge the bit lines to VDD. You have a write driver, which on the enable signal will pull either bit or bit bar to 0. We have a bit sensing circuitry, and this circuitry can either be a large signal sensing or a small signal sensing. We look at both. Large signal sensing is generally used in small arrays, whereas small signal sensing is what is the norm and it's used in almost all SRAM and DRAM arrays. And finally, we have column muxes, and column muxes are used to improve the area utilization in the array. So bitline conditioning normally consists of just two large PMOSes, and these PMOSes are used to basically precharge the bitlines to high. So let's look at the organization of the SRAM when it has local and global word lines. So we know that the bit line swing from VDD to ground in this case. The local bit line is connected to say B bit cells. So that would look something like this, where you had the local bit line 0 connected via the access transistor through the SRAM cell. Right. Now, this gate looks like a unfooted domino gate, right? So you have the precharge here, and then you have these various pull down NMOS transistors. Because again, the read is going to essentially pull down bit or bit bar depending on whether a 0 or a 1 is stored inside the cell. And so when you have a lot of pull down nodes connected to this large capacitance, this bitline capacitance is a floating capacitance. We normally connect a keeper transistor to it to ensure that we reduce the noise at this node. Now similarly, what we can think about is that multiple such local bit lines can be ORed together to a global bit line, right? So you have this OR function here, which is going to convert multiple local bit lines into the global bit line. And again, the global bit line also looks like an OR, dynamic OR. And so therefore, to ensure that this node again is less sensitive to noise, we add another keeper to the global bit line. Right? And now because this looks like an unfooted domino, the inverter that we are going to use to actually read out the output signal can be a high skew inverter, because the falling transition as the input is the one that is more important to us. Now, the maximum number of transistors that are connected to any bit line are going to be limited by what is the maximum leakage I can tolerate at the bitline node, right? And so the worst case for leakage is going to be when the cell to be read is a 0, but all other cells are a 1. So that would be the worst case leakage for the bitline, and from at that point also we want to be able to read the 0. So already the rest of the transistors are pulling down the node. In addition, we have the 0 which needs to be read off it. Now, small signal sensing is another method by which we do a read, right? So in the previous cases, what we have seen is that the bit line has to swing from VDD to ground when you're reading a 0, either the bit line or the bit line bar. Now, because these bit lines have a large capacitance, because you have multiple cells connected to them, swinging these lines to VDD and ground is going to consume a lot of power. So one way to reduce that power would be using what is known as small signal sensing, in which we access transistors are activated only long enough so that we see a separation between bit and bit bar, right? So eventually we are looking at a separation between bit and bit bar to decide whether we have a 1 or a 0 in the cell. And so once we are assured that the separation is large enough that we can now call it a 1 or a 0, we then assume that the voltage is sensed, and then the word lines are turned off, so that way we reduce the leakage associated with the bit line. Now to do that, we basically need a differential amplifier. So you can imagine that output of bit and bit bar are connected to this differential pair, and then you use a differential amplifier to sense the output at the bit. Okay? Now, if you look at this is the analog version of the sense amplifier, and the analog version is going to consume significant amount of DC power because there's a constant current, the bias current that's going to be flowing through both arms of the circuit. And secondly, as your VDD scales, it becomes hard to bias the circuit in saturation because of the fact that your overdrives are going to be limited, right? And so this circuit has an issue. So what we do typically, because again here we are sensing only 0 and 1, we don't really care about small signal. What we do is we sometimes use a clocked sense amp, which again consists of a back-to-back connected inverter. So the back-to-back connected inverter again is a circuit we know which can quickly flip from 1 to 0 depending on what is the noise associated with that particular node. So what we are trying to do here is we are using the difference in these two to flip the inverter to either position of 0 or 1, and that would sense the output at the bit. And this regenerative feedback is the reason why this circuit works. And now this circuit doesn't require a lot of biasing, it's a digital circuit. So all we care about is ensuring that the transistors are turned on and the back-to-back inverter takes care of the rest. Now to ensure that the bit line capacitances here are not affected by the rest of the SRAM cells connected to the bit line, we use isolation transistors. So essentially we charge up this node, and then during the sense we cut off this node from the rest of the bit line to ensure that when we're swinging this node we don't have a large capacitance to swing it, and therefore you get a faster sense amp operation. Now power dissipation in such a case is therefore reduced for read operations by turning off the word line once we develop a sufficient differential signal. So the key is to identify what is that minimum differential signal that needs to be developed, taking into account all the various noise sources or variations that might occur in the SRAM. And once you do that, then you design for that difference and then design the sense amp for that particular difference. Now, what are some of the design considerations when it comes to the sense amp? So remember, the sense amp has to be susceptible to differential noise at the bit lines, and it has to detect a voltage difference, right? So that is the goal of the sense amp. So we need to ensure that the pre-charge is long enough. So to begin with, we need to make sure both bit and bit bar are as matched as possible, right? So therefore, we want to ensure that the pre-charge is long enough that these large capacitors, which are the bit lines, are charged up both to VDD. And we typically use what is known as an equalizer transistor between the bit and bit bar to ensure that both the nodes are charged up to the same high voltage value. And now what might happen is, remember, this SRAM is a very dense array. So transitioning bit lines adjacent to your bit line might introduce noise, right? And so we have what are known as various ways of laying out the bit line so as to reduce the coupling noise between the bit line that you care about and all the other bit lines around it. And these are done by using what is known as twisting or transposing lines. So you sometimes do layouts which are twisted layouts, or you sometimes share multiple metal layers to create a bit line, and that ensures that you have minimal noise coupled between the bit lines. The other important thing about coupling is, while you want to reduce the coupling between one bit line and the adjacent column bit line, improving, or rather you want to equalize the coupling between the bit and bit bar, so that way you assume that whatever noise is induced in your bit, the same is induced in bit bar, so that your sense amplifier is now only sensing the difference. Because otherwise, if the noise is coupled to only one of the bit lines, then the sense amp is going to respond to that noise difference too. Other thing is the sense amp, by definition, because it consists of cross-coupled inverters, or if you use the analog sense amp, is going to have some mismatch between the transistors, leading to a differential offset voltage. So when you are picking what is the voltage at which we say that the bit and bit bar have differentiated, this needs to be taken care of. That is, we have to overcome the offset voltage that might be present in the sense amp. And the offset voltage obviously is a function of the process variations and also of BTI. So this becomes important to characterize when you're deciding when should the differential voltage be set so that it is a read operation. And finally, the timing of the sense amp is very essential. We want to ensure that we trigger the sense amp at the right time so that the bitline voltages are sufficiently different. If you trigger it too early, it is possible that we might respond to noise signals in some of the worst case. And if you trigger it too late, then essentially your SRAM is slow, plus it creates more power consumption, right? And so to ensure this, basically a lot of the trigger signals or the control signals of the SRAM need to be timed properly so that they are delay matched to the access path or the decoder path, etc. Right? So there's a lot of delay matching that needs to occur when you're designing the SRAM. Now let's talk a little bit about the leakage in the SRAM. Remember, as I started, I told you that memory is a large component of the SoC or the processor. And so therefore, because this is consuming a lot of area, we need to have a control on the leakage that is happening through the SRAM bit cell. So let's look at the various leakage components that are happening in this bit cell. So again, if you see here, this is a 6 transistor bit cell, consists of 2 PMOS transistors and 4 NMOS transistors. Now let's assume that we have a 1 stored in the SRAM bit cell, and let's assume we're looking at leakage, so that when we're not really using the SRAM, so let's assume that bit and bit bar are pre-charged to 1. So this is a bit cell which I'm not being used, but this still contributes to performance because this is going to create a leakage current through the bit cell. So the first leakage current is the subthreshold leakage current that I will have in this transistor because its output node is 1. And I will also have a subthreshold leakage that's happening through A1 because I have a pull down path from via A1 and D1. Similarly, I'm going to have subthreshold leakage that is going to be happening in this inverter also. So these two inverters contribute to the subthreshold leakage of an inverter, that is the regular inverter. Additionally, you have the subthreshold leakage through one of the access transistors. And then you have gate leakage and source drain leakage between all the various gates and the substrates. Now, with the use of high K, the amount of gate leakage is reduced, but remember that as you use the SRAM, BTI kicks in and that ends up creating slightly higher levels of gate leakage in your system. And so we need to account for all leakage mechanisms that are possible in the SRAM. So one of the primary goals of designing the bit cell is to ensure that the leakage in the SRAMs is as low as possible, and as the size of the SRAMs is going up and as you're scaling technology, SRAM leakage, as expected, continues to be a higher problem to manage. And so we then talk about using differential VDDs in the SRAM or shutting down the SRAM when not in use, etc. so as to arrest the leakage in this structure. Next step we'll talk about is types of SRAM cells. So we just looked at a 60 cell. Now 60 cell is the most common cell that is used in SRAMs, primarily because of the fact that it is the densest layout. Now in addition, if you look at the SRAM, we use an SRAM because it allows us to have a higher bandwidth memory. And so sometimes we want to create what are known as multi-port SRAM. So if you look at the current SRAM bit cell, the 60 cell, it has the same read port and the same write port. So the same bit and bit line are used to both read and write into the cell. Now sometimes we want applications where we want to do a simultaneous read and write, in which case we want to have multiple ports so that I can read and write through various pins to the bit cell. So these multi-port SRAMs are typically designed either to give you a bigger design window or to improve the bandwidth of the cell. So the trade-off is normally the area of the cell. So we'll see that most of these higher order SRAM cells are going to have a larger area. The transistor count is going to go up. So just to recall, there are two important ratios in the SRAM bit cell. One is the beta ratio, which is the ratio of the pull down to the access transistor, and we want beta to be as high as possible for read stability. The other ratio is known as the gamma ratio, and the gamma ratio is the ratio of the access transistor W/L to the pull up transistor W/L, and again we need this to be as high as possible, and we need this to be as high as possible to improve the write margin of the cell. So we're going to look at two particular SRAM bit cells just to give you a flavor of the various kinds of bit cells around: the 8 transistor cell and the 10 transistor cell. So the first cell we look at is a 8 transistor cell, which basically consists of the 60 SRAM, and in addition to that we have 2 additional NMOS transistors connected, and we have what is known as an additional read port for the cell. So in addition to the word line is essentially 2 word lines, you have something known as a read word line and a write word line, and you have a write bit line and bit line bar, and in addition you have a read bit line. So what you've done in this cell is you've essentially separated the read operation and the write operation, And we had looked at initially when we were discussing the 60 cell that the read and write are intimately coupled in a 60 cell, because you cannot, if you increase one, it affects the other and vice versa. So in this case, what happens is, since you're separating the read path from the write path, you have a larger design window to ensure that you get a good read margin as well as a good write margin. And so what happens is, because you have this different read word line, you can boost the read word line to improve read speeds. You can also boost the read bit line again to improve word speeds, and hence increase the I cell. I cell is nothing but the current that flows in the cell when you're reading. And so if the I cell is increased, then the bit line separation is going to go up, leading to a faster sense amp and a faster read. The other thing is, because we now have a read bit line, we don't really need to pre-charge, because directly by looking at the transition on the read bit line, I can decide if I've stored a 1 or a 0 into the cell. So because I don't have to pre-charge these cells, I reduce the power that is consumed in the read operation. And finally, one way to improve the write margin is to suppress the word line voltage during the write, so as to weaken the pull-up transistor. Now what happens is, we don't have an issue because of the fact that the word line is separated from the read line. We can now work with suppressed word line voltages for write margins. Similarly, we can add 2 additional transistors and create an even larger bit cell, and this is known as the 10T SRAM cell. Now the 10T SRAM cell consists of 2 different paths for the write and read. So for the write operation, we have a row decoder and a column decoder. And for the write operation, the pull down consists of these 2 transistors. This transistor, which is selected using the column, and this transistor, which is selected using the row. Similarly, if you look at for read, the read consists of 2 transistors, and this read transistor here, this pull down transistor here, is separated from the bit cell pull down transistor. And so therefore this can be optimized independently of the SRAM noise margin and the write margin. So this controls the write margin, this controls the read margin. And so what happens is, you've essentially eliminated the issue of the read margin, because you've created a new pull down transistor for the read. Right? So this essentially eliminates the trade-off between read and write and gives you no issues with read. So this cell, even though it's larger, is very efficient for read operations. So what we have done is, we have separated the drivability requirement of the NMOS for the read and write by creating 2 different paths, and hence we can size them independently. And so that means that we can size up both beta and gamma higher, and that essentially eliminates the trade-off we have with the SRAM noise margin, write margin, and the cell current. Obviously, the drawback with this would be a much larger area of the bit cell. Additionally, the peripheral circuits are going to be slightly more complicated, so you need more circuitry in the periphery. Now, before we wind up, let's just talk about scaling of SRAMs. So again, I'll recall the performance metrics of the SRAM include speed, power, and area, just like any other digital circuit. Now, what has happened is, because SRAM area is one of the smallest cells, if you will, it has very high utilization of transistor to area ratio. Previously, what has been happening is, SRAM area has been scaling consistently with logic over the last 2 decades or so, and hence, SRAM performance has been continuously improving. But over the last 5-6 years, this SRAM speed, or the SRAM speed up, has slowed down. And there are multiple reasons for these. Some of the primary ones are that dimensional scaling in transistors has scaled down, and because the SRAM is such a dense and such an area heavy cell, because there is less dimensional scaling, the overall power and performance and cost of the SRAM is increasing. Second issue has been that as we have ended up scaling transistors, process variation has gone up. And so with increased process variation, what has happened is that the Vmin of the SRAM is not reducing. And that means that the smallest VDD that you can reliably operate the SRAM has not been scaling as fast as the logic VDD. So this means that this leads to power consumption SRAM getting sealed. And the last thing is that the reliability of the SRAM is reduced too, and so that means that you have to have a lot of error correcting codes, etc. So the peripheral circuits have started increasing. So the overall area of the SRAM block, for example, even though the memory area, so one, the memory area is not going down as fast as it should, and secondly, you're increasing the peripheral circuits in the SRAM. So overall, the SRAM size is not scaling as much as logic. And so what are the ways people are looking at? So you see now that SRAM performance purely does not come from scaling. And so you have to employ other techniques to improve SRAM performance. So a couple of things which are already been done in some of the recent ISSCC papers would be differential VDD for the SRAM and periphery, and then having put the SRAM in the sleep mode. So basically, when you're not using the SRAM, try to reduce the VDD to as low as possible so that the SRAM retains its state. But by reducing the voltage on the SRAM, you reduce the leakage current in the SRAM. There are also other interesting techniques like using negative bitline voltages and transient voltage collapse, which can be used to enhance the low voltage operations. Again, the goal here is to reduce the power consumption in the SRAM because of the fact that high bandwidth, you're continuously accessing the SRAM, so you want to ensure that you operate it as at low voltages as possible without really sacrificing for the margin. And finally, there are a lot of process improvements that are ongoing and have already been placed. Things like double and triple track metal wires to reduce the coupling and to increase the resistance of reduce the resistance of the bit lines. And then the use of the buried power rail, again, that helps with improving the area efficiency of the SRAM.